So here we have to analyze this sequential circuit. But just before starting analyzing, I just told you one step that I forgot in the previous exercise. I told you that we are going to work with synchronous circuits. So there is one thing remaining here. We have to add the clock. The sequential circuit, the memory element, is going to work with a clock. So imagine that we are working with a, for example, JK bistable triggered by rising edge. So triggered by the rising edge, this was the symbol. So we have here the clock of the bistable. And you cannot forget this, because if you forget the clock, the circuit doesn't work. So just have be careful with this, because we always have to insert the clock signal into the bistable to make it work. So sorry, because I forgot this, and it's quite important. And you have to use here the symbol that corresponds to the kind of clock you have. So now we are going to start analyzing the circuit. We have this sequential circuit, and we have to analyze the circuit. That means to obtain the state transition diagram that allows us to understand how it operates. So the first step, we go to the slide of the analysis of synchronous sequential circuits. The first step is to identify the input and the output and determine the number and type of memory element, establishing the present state or current state and the net state variables. So we are going to go to do that. So step 1. So the inputs are x1 and x0. Sorry, x1 and x2. The output is here. I forgot to write it. The output is here. So the output is C. And the state variables, I told you that each memory element is going to store a state variable. Here we have the memory elements given in a generic way. We can modify them slightly to have our specific state variable. The kind of memory element, we can see that they are SR bistable. So I'm going to remove this to directly write the name of the state variable I'm going to choose. This is going to be, for example, my first SR bistable with the state variable A1 and Y1 negated. You can use, for example, Q1. There is several ways to name the bistable. So if this is my first bistable, this is going to be, for example, my second bistable. The state variable you're going to store is going to be, for example, Y2, and we have always the variable and the variable in its negated version. So if we look at the clock signal, we can see that we have SR bistables that are triggered by rising edge, just looking at the symbol we have in the block. Okay, so we have finished the first step. The second step is to specify the output and excitation function of the memory element based on the input and the current state variables. So we have to get the equation of the net state variables and the output variable as a function of the input and the current state. So we have to obtain this function here, this function, the output, and we have to calculate this. You remember that we obtained this from the excitation table. It was the last stage of the design of a sequential circuit. So remember that we are doing the step in the opposite order. So this is quite confused because we have a lot of cable. I suggest you to use colors. I normally use color because it helps me to identify the path. So for example, here in this AND gate, what we have is the negated output of the second SR base table. Here in this AND gate I'm going to use a different color. Here we have, for example, the state variable not negated of the second base table. In the other gates we have, for example, here the negated state variable of the first SR base table, and here we have the state variable not negated of the first SR base table. So we are going to obtain the excitation functions that are S1, R1, S2, R2, and the output. So we start with S1. S1 is here. It's a AND gate. You can see that here in this input we have a circle. The circle always means the inversion of the variable. So in this AND gate we have X1 but negated, and the other input is Y2 negated. In R1 we are here, we have X2 negated because we have this small circle in the input of the AND gate, and the other input is Y2, the state variable of the other base table. In S2 we have X2, in S2 we have X2 and Y1, and finally in R2, sorry, in S2 we have Y1 negated, and in R2 we have X1 multiplied by Y1 non-negated. And what's the output? The output is directly Y2. So looking at the slide, we already have the functions, and now we have to build the excitation table. That was the last table that we built when designing a circuit. I have a question here. You know that when you are designing a sequential circuit, in the first stage you have to choose between a Mealy machine or a Moore machine. You know that sometimes you can use the one you prefer, but one of them is more intuitive or is more appropriate for the circuit you have to implement. In this case, how do we know which machine use the person that designed the circuit? We have to pay attention to the output. The output is C, and it depends of Y2. Y2 is an input or is a state? It's a state. It's a state variable. So this output only depends on the state variable and not on the input. If we go back in the topic, so when we saw the sequential machine, the Mealy machine, in the Mealy machine the output depends on the state variable and on the input. So that's the case? Not. In our case, the output only depends on the state. So this is a Moore machine. A Moore machine because of that. And we have to know this because the tables have slightly different version depending on the machine we have. So we have identified here a Moore machine. Just because the output is this way. If the output would be, for example, this could be a milli machine because we have the input there, but that's not the case. So now we are going to continue building the excitation table. Remember that the excitation table relates the input of the bistable and the behavior of the circuit that we are designing. So in this circuit we have 2 inputs and 2 state variables. So we are going to have a table that is going to be a Carnot map of 4 variables. Let me draw this. So now we have here the excitation table that we have to fill. I have used just one table for the both of the bistable we have. You may use 2 tables, or in fact 4 tables, one for each input. For example, one for S1, another table for R1, another for S2, and another for R2. Here we are going to use, as I said, the same table, so we have to be, careful. So remember that when we were designing a circuit, we have the excitation table and we minimize the function and we obtain the equations. But here we have the equation. It's the opposite. We have the equation here and we have to fill the table. So we are going to go little by little. We are going to start with S1. That is going to be the first value of the table. If we are here in S1, we are going to have ones in the cells for which x1 is 0 because it's negated and y2 is 0 because it's negated. x1 is 0 here and here, and y2 is 0 here and here. So we are going to have ones in these values. And the rest are going to be 0. So this is the excitation table of S1. Now we proceed with R1. So we are here. In R1 we are here. So we are going to have ones when x2 is 0 because it's negated, and y2 is 1 because it's not negated. x2 is 0 here and here, and y2 is 1 here and here. So we fill the table in those cells with ones, and for the rest of the table we are going to have 0. So we already have S1 and R1. So we are going to design the values of the other inputs for the second SR bistable. So for S2, we are here, S2. S2 is going to be 1 when x2 is 1 because it's not negated, and y1 is 0 because it's negated. x2 is negated here and here. Y1 is not negated. Sorry, I did it the opposite way. x2 have to be 1 because it's not negated. x2 is 1 here and here, and y1 is 0 here and here. So in these places we have the ones of our function. And the rest of the cells are 0. So I'm going to start again because I think that I was making a mistake. As I told you, sometimes I'm doing the exercise in the tablet, so I have very little space and sometimes it's confusing for me to see the values. So sorry for that. I'm going to start again with S2. With S2, with S2 we are in the case in which x2 is 1 because it's not negated. X2 is 1 here and here, and y2 had to be negated because had to be 0 because it's negated. y1 had to be 0 because it's negated. y1 is 0 here and here, so in this case our ones are going to be there, and the rest of the table is going to be 0. And finally we have R2 that is going to be 1 when x1 is 1 and y1 is 1. x1 is 1 here and here, and y1 is 1 here and here, so we are going to have ones in these cells, and the rest are going to be 0. So now with this we have finished the second step in which we obtain the excitation tables. So we have to go to step 3 in which we build the state transition table. This is the transition table that we are used to build. The transition table are going to have the same size of the excitation table, as you can remember, but instead of having here the input of the bytes tables, we have the net states, the net state values. So I'm going to make some space here. I'm going to need the excitation table, so the number of the cells are the same. Here we have our state variables. We use our typical gray code. And we need the behavior table to fill this table. The behavior table of the SR bytes table was the following. I remember that you need to know that from heart. So inputs 1 1 are not allowed. With 0 0 we keep the previous state. This one. With 0 1 we reset the system, and with 1 0 we set the system to 1. So we have to look to the excitation table and to the behavior table of the SR to fill the transition table. So here, remember, we have to write the transitions between the current and the net state. So we go row by row again. So for y1 is this. For y1 is the state variable of the first bytes table. This one, okay? So we have to look at the values of S1 R1. So if y1 is 0 and the input of the SR base table are 1, 0, the net state is going to be 1. So I write a 1 here. If the input is 0 and we have a 1, 0, in all these cases we are going to have a 1 because we are in this row. So for all the 1 zeros we are going to have a 1. If the input is 0 and now we have a 0, 0 in, sorry, I choose the other function. If I have a 0 here and the input are 0, 0, we keep the state. The state is 0 because we are starting here. So we write a 0 here in those cells in which we have 0, 0. So now we have that the input is 0 and the combination in the input of the base table is 0, 1. In 0, 1 we are going to reset the system, so the output is going to be 0. We have another 0, 1 here, so the input is going to be 0 as well. And here we have 0, 0. With 0, 0 we keep the state. So if the state is 0, then the state is going to be 0 as well. So now we are in the case in which the current state is 1 and we receive 0, 1. With 0, 1 we are here, we reset the system, so the net state is going to be 0. If we have a 1 in the current state and we receive a 0, 0, we are keeping the state, so we have the same 1. So if now the input, well, the input is 0, 0 here, so we keep the state, we have a 1, and here the input of the base table is 0, 1. With 0, 1 we reset the system, so the output is 0, the net state is going to be 0. And finally we are here, the current state is 1 and we have a 1, 0 that is setting the system, having a 1, the net state. Here the input is 1, 0, so it's the same. We set the system, so having a 1. Here we have 0, 0, that means 0, 0 means to keep the same state. Looking at the behavior table, if the state is 1, we keep the same state. And finally we have a 0, 0 that is the same, it's just keeping the state. Keeping the state. So we keep the same state, that is 1. So this is for y1. So now we have to look at the state variable of the second base table. So here we have 0, sorry. Here we have 0 and we have this combination and the input, that is to keep the same state. So we keep the same state 0 for the net state. We have 0 as well here, so we are going to have the same value, and here as well. No, sorry, here we have a 1, 0. Here we have 1, 0 and 1, 0, and for 1, 0 we have a 1 because we set the system. So 1 and 1. I'm going to go a little faster because otherwise it's going to be eternal. If y2 is 1 and we have 0, 0, in these two cases we keep the state, so we have the same value, that is 1, 1 and 1. In the other cases we have 1, 0. When we have 1, 0, we are setting the system, so we have a 1. So here we have that y2 is 1, and we have the input 0 0 0 0 here. 0 0 is just keeping the same value, that is 1. And in the other combination we have 0 1 and 0 1. 0 1 is resetting the system, having a 0 in the next state. And finally y2 is 0, and we have 0 0 here, 0 0 here, that is keeping the same state. Looking at the behavior table, if the state is 0, we keep the same state. And here we have 0 1 and 0 1. 0 1 is resetting the system, having a 0 in the next state. So we have finished the transition table. Once you understand this, it's quite fast, but I just explaining it little by little. It seems slow, but it's quite fast. So the transition table. We have finished the step 3. Step 3, finish. And now we are going to have the state output table. The state output table. Okay. So remember that we don't know the original name of the state that the designer chose. So we are going to invent the name of the state. We have 4 states. The system has 4 states. Why 4 states? Because it has 2 state variables. So 2 state variables that codifies 4 states. Muy bien. Sorry for the Spanish. Very good. We are going to continue. So this is, remember, this is a this is a Moore machine. In a Moore machine, we have this state output table. We have that the output only depend on the state. So we are not going to add the output in each cell. We are going to use only an extra column for the output. So the state output table is the same. Now remember that in this table we didn't use the codification of this table. We used the name. Sorry, I'm saying stable. I'm mixing because of the tiredness, but I hope you understand me. Otherwise, ask me in class or in tutory. In this table, I was telling you that we have the name of the state, not the codification. So we have for a state and 2 inputs. Here we have the state, and for example, I'm going to call the state A, B, C, D. A, B, C, and D. So copying the transition table is just copying the transition table using the names of this table, of the state, sorry, and adding an extra column for the output. And here we have the combination of the input. So looking at this, at the transition table, if the net state is 1 0, 1 0 is state D. If the net state is 1 1, 1 1 is state C. 0 1 is B, and 0 0 is A. Here we have that 0 1 is B, 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 and B. C, we have 0 1 that is B, 1 1 that is C, 1 0 that is D, and 0 0 that is A. And in the last row, I'm looking at the rows, okay? Just in case you are lost. And for the last state D, the next states are 10, 10, 10, 10. That is the same state, D. And what happened with the value of the output? Remember that the output was the state variable y2. So the state variable y2 is in this column. So this is going to be the values of the output, because according to the analysis of the circuit, we have this. So copying these values in the column of the output, we have 0, 1, 1, 0. So we have finished the state output table. That is the step 4. And finally, we are going to build the state transition diagram. We have how many state? 4 from A to D. So I have to use 4 circles, 4 nodes. We have the following. We have that we are in a, remember here, we are in a Moore machine. In a Moore machine, the output only depends on the state. So in this case, we have the output inside the nodes. For A, the output is 0. You can check it here. For B, the output is 1. Here. For C is 1, and for D is 0. For C is 1, and for D is 0. So the output is inside the nodes. So in the arcs, we are going to have only the inputs. I remember that you have to add this arc to show the reader the meaning of the arcs. So we can complete the state transition diagram just looking at the state output table. If we are in A and we receive a 0, 0, we go to state D. You can see it here. We go to state D if the inputs are 0, 0. If the inputs are 0, 1, we go to state C with the inputs 0, 1. If the inputs are 1, 1, we go to B. And finally, if the inputs are 1, 0, we keep in the same state A. So second row, for all the inputs, we are going to be in the same state B. So we state in the same state B for all the inputs. We can write all the combination or just use X. When using X, it means that the variable can be 0 or 1. So this means that we have all the possible combinations. So if we are in C and we receive a 0, 0, we are going to go to B. If we are in C, if we receive a 0, 1, we are in C. If we receive a 1, 1, we go to D. And finally, if we receive a 1, 0, we go to A. For the case of D, we have the same as for the state B. For all the combination of the inputs, we are going to be in the same state for all the combinations. So we can use X. For all the combination, we are there. So we have just finished the analysis of the sequential circuit because we have just fulfilled the fifth step. So we start from the circuit and we are doing the different steps, obtaining the different tables, and we obtain, sorry, I moved that, the state transition diagram. So we have finished. This is the first analysis that we carried out in class, but we are going to do more exercises of analyzing this kind of circuit. So I think that we can finish this lesson because I don't know the time, but I think that I have spent quite a lot of time. If you have doubts, just ask me in messages through the virtual campus in the class, because sometimes I have to see this very near. I don't have space to see it, and I make mistakes. So if I may have some mistake. I may make some mistake. If you identify a mistake when following the exercise, just tell me. I try to do it well, but we have a lot of things here, and I can see well with the table. So I hope this video is helpful. See you in class. Bye.